Hello, everyone, and welcome to this next session on our discussion of the molecular spectroscopy of various molecules. We're going to talk today about infrared spectroscopy, otherwise usually known as FTIR, or Fourier transform infrared spectroscopy. It's really just a technique based on the vibrations and rotations of a particular molecule. You may recall from our previous sessions where we discussed the vibrational energy levels of a particular molecule. We discussed the idea of electronic vibrational energy levels, which would be the ones that we would be encountering in UV vis spectroscopy. Those are quite high energy transitions. That's why they're usually found in the UV and visible range of the spectrum. Here today, we'll be talking a little bit about the ranges of infrared spectroscopy, especially getting on to where it applies to the mid-IR. So these transitions typically are much lower in energy than the electronic transitions we saw in UV vis spectroscopy, but that does not make them any less useful. They are in fact very useful, and in some respects, FTIR and infrared spectroscopy in general is one of the most useful techniques in correctly identifying a particular molecule, especially if we need it to be done very quickly and we need a high degree of accuracy. So it's still ultimately, though, based on this idea that we had in the UV vis spectroscopy, where there's some sort of absorption going on. The absorption in this case is going to be the absorption of energy in a vibrational or rotational state. So we're going to talk about what vibrations are, but basically they're the movement of two atoms which are close together, two atoms which in chemistry we say are bonded together. So this molecular absorption spectroscopy is really fundamental to a lot of what we'll be discussing. So MAS results from the absorbance A or transmittance T of a solution in a transparent cell having a path length B. So this is the absorbance that we get from our solution. So in the case of infrared spectroscopy, the energies we use are much lower than those in, for example, the UV vis spectroscopy, but they're still nonetheless very useful. Now, we have, so to speak, these transitions happening even without us really knowing that they're happening. So in the case of UV and visible, we need to really give a lot of energy. In these cases, the molecules are still vibrating even if we're not actually giving them energy. They normally get enough energy just from heat energy of the universe. So where do we do these kind of measurements? Well, in UV vis spectroscopy, IR, Raman we'll talk about after we're done with infrared, HPLC detectors, and so on. HPLC detectors, though, are really just a subset of UV vis detectors. So typically it's all based on the Beer-Lambert law. So the Beer-Lambert law we saw and discussed previously. So this is where the absorbance is equal to minus log T, or it's equal to the power of the different beams, either the incident and emergent beam, or in its most common form, it's going to be epsilon BC, where epsilon is the molar extinction coefficient of a particular species. B is the path length, and C is the concentration of the analyte of interest. Remember that the epsilon value can change based on the wavelength and obviously also based on the particular absorbing species. So why might some of these things not be true in practice? We discussed this back whenever we discussed the Beer-Lambert law before, but there are many different things which can cause the absorbance not to be linearly related to the Beer-Lambert law. Some of these things can result from, for instance, interactions of the two molecules with each other, or well, of the absorbing species with itself. So measurement of absorption or transmission. So how do we go about this? So usually we want a beam which is only going to be attenuated by the sample. So this really means that it's not going to be affected by the solvent. It's not going, like the beam that goes in, the beam that is incident on the sample container doesn't actually reflect off of the surface of the sample. So there's no reflection there. And typically this is pretty hard to do. Usually there is some reflection. It's better if you do it at 90 degrees. So basically at right angles. So if this is the wall of my thing and my light is coming like this, it's at 90 degrees and kind of a T shape. that's probably the best way, but still, even at that, there is a certain degree of reflection which happens. Then we have scattering in solution. So this is where there maybe is some dust in solution or some very fine particles that we weren't able to totally remove. There are a lot of different things which can happen as we go through, which can cause the sample or the beam which enters the sample and the beam which leaves the sample to be effectively or to be not only attenuated by the sample but by other things. To overcome this, we use a blank. So we have this setup here where we have the absorbance is equal to the log of the power of the solvent over the power of the solution, which is equal to log of P0 over P. Transmittance then is equal to the power in the solution over the power in the solvent, which is approximately equal to P over P0. So here is a schematic over here, a diagram which shows two of the major areas of loss, which are scattering losses and reflection losses. Beer's law also applies when there are more than one absorbing species, assuming they don't interact. So we've talked about this as well under UV vis, but it also is applicable here. Now, you could, in theory, use infrared spectroscopy in the same way that you use UV vis spectroscopy. However, it's typically not done. Typically, whenever we're using infrared spectroscopy and infrared molecular absorption spectroscopy, what we're actually looking for is really the identification, because that's where the power here lies. Because if we think about a molecule, there are a lot of different atoms which are bonded together. Those bonds all have different vibrations, and so a particular set of vibrations will give a kind of a fingerprint for a particular molecule, which is not present in our UV vis spectroscopy. Our UV vis spectroscopy is really well suited for the quantitation or how much of something there is there, but it's not really suitable for identification. I mean, you can use it in a pinch, but it's going to be not as accurate as some other techniques like infrared or even NMR or Raman spectroscopy. Raman spectroscopy is actually really good for identification of pharmaceutical molecules as well. So there are three main regions in the infrared spectrum. We have the near infrared, we have the mid infrared, and we have the far infrared. So the near IR, MIR, and FIR. Usually whenever we're talking about these things, we just say near IR, IR, and FIR. Usually mid infrared is just basically just called infrared. It's the most commonly used. It's the one where the absorbances are easiest to define. So this is the total electromagnetic spectrum. This is a zoom in on the infrared spectrum. These are the wavelengths in microns, which is sometimes used in infrared spectroscopy, especially in older literature. And for a lot of like compounds that are commonly quantitated or looked for in infrared spectroscopy, especially in terms of analytical use, a lot of the data that you'll be looking up will be in older literature. So here we have the region breakdown. So region, wavelengths, wave numbers, frequencies. So near IR is from about 13,000 to 4,000 wave numbers. Mid IR is from 400 to 200, or 4,000 to 200, and far IR is from 2,000 to 10. Most used from 4,000 to 670, so almost totally in, no, it's all in the mid IR. Usually we don't go, like the limit of the mid IR is about 200 wave numbers, but typically we only go to about 670 wave numbers. So this is because it's the spectrum starts to get a lot more complex in what's called the fingerprint region. It's especially complex for organic molecules, but saying that, there's still a lot of important information which can be gleaned from your spectrum in that region. So it's not just something you should discard, but certainly up to 4,000 is very important. Up to 4,000 is important because a lot of the absorbances of things like water and things like alcohols, anything which has got an OH group, a lot of those absorbances happen there. Other things which absorbances that are in that region sort of like really like kind of good markers for the presence of a compound. Things like nitriles, things like so CNs. Then we have CO bonds, we have double bonds and single bonds. Those all kind of happen in that sort of region of about 1500 to 4000 wave numbers. So near IR, NIR is measured with spectrophotometers similar to UV vis spectrometry. Quantitative analysis of agricultural and industrial methods is the main use here. It's pretty good for like high throughput, quick measurement of samples to see if something is present or not, and then it can be further analyzed. If we get a positive result, we can potentially try and measure that sample in a different way. So it can also be useful for certain governmental agencies or whatever who are looking for illicit drugs in particular samples or something, or they're trying to find it on a piece of fabric or something. I don't know. It's a really useful technique. Then we have mid-IR, which is useful for complex samples. So I've talked a little bit about that already. We will talk a lot about mid-IR. And then FIR was previously not really used. And it was pretty limited. It was pretty hard to get spectrometers in that region, but it's definitely not possible. Although most of the measurements still occur in the mid-IR. So here's a typical IR spectrum of hexane. So that's this molecule down at the bottom. So it's got 1, 2, 3, 4, 5, 6 carbons in a chain, all with single bonds, no conjugation. And we have two spectra here. We have the absorbance spectra and the transmission spectra. So oftentimes you'll see the transmission spectra and sometimes you'll see the absorbance spectra. It just really depends on what we're dealing with and who's reporting it. So you can see the CH stretch and its present. So for example, if we wanted to view this stretch here, it's going to be much better in the absorbance band, whereas here, if we've got the transition band, the transition spectra, sorry, the CH band is going to be much better to view here. But both of these represent a CH stretch, so a carbon-hydrogen bond stretching or bending. So this is a stretch, so it's kind of like moving closer and further away from each other, and the bending is kind of a twisting. And so we end up with different wavelengths for those different transitions, different wave numbers. So, okay, so we've talked a little bit about the IR and seen two sample spectra in transmission and absorption. We've talked a little bit about how it's somewhat similar to UV vis, albeit we're looking now at vibrational and rotational transitions, usually in the ground state of a molecule. So what causes an IR signal? So I've told you it's the vibrational energy levels, but why are there different absorbances for different molecules? Why are there different transitions? What is it that's causing this? And it's ultimately down to the changing in the electron cloud or the electron density around a particular bond into what's called a dipole moment. So IR radiation is too weak to cause transitions, but seen in the UV vis, only molecules with small energy differences between the vibrational and rotational levels absorb. So what does that mean? So it's kind of like talking about this idea that we're not giving it huge amounts of energy. Remember, some of the transitions back in the UV vis, those were too high in energy. They were destroying the bonds if we try to measure them. That's not possible here in IR. None of the transitions in the IR will actually lead to the destruction of the molecule. So typically we're dealing with the ground state molecule here. There's no excited state to deal with, except in the sense that there is an excited vibrational state and also rotational state. Usually like another term for infrared spectroscopy is vibrational rotational spectroscopy. So the vibrational and rotational lines are kind of intertwined because they have very similar energies. To absorb IR, the dipole of the molecule must change during the vibrational rotation. So what is a dipole? A dipole is kind of like, so hopefully you realize that atoms have electrons, and those electrons are shared whenever we form bonds, like covalent bonds and things like that. So if those electrons are shared unequally between the two molecules, then what can arise is a localized positive and a localized negative part of a molecule. And so that can cause the absorbance, or that can allow the absorbance of IR. So this dipole moment is determined by the size of the charge difference and the distance between the two centers. So really what this is just a fancy way of saying that on one of the atoms, there's more negative charge than the other, and how far apart are they? If the frequency of the dipole moment matches the IR radiation, then absorption happens. So this is similar to the UV vis. We scan across all of the different wavelengths and different wave numbers, and then we see where the absorbances happen. Typically, what you have in an FTIR spectrometer is an array photo detector array rather than a single wavelength monochromator, because usually you capture the whole spectrum in one go and then average it over multiple scans. So rotations of asymmetric molecules also causes a change in the dipole moment, but these absorptions are weaker. So if a molecule is not totally symmetric. So dipole moment, so here is a fancy, well, not a fancy, this is just a schematic. So we've got a positive and a negative part. So we've got the positive and the negative part going through the dipole moment. You can choose whichever side you want to be positive and whichever side you want to be negative. But basically one side is typically going to be more negative than the other side. When atoms and molecules do not share electrons equally, a dipole moment is created. And this is caused by different atomic electronegativities. To be a polar bond, there must be a large difference in electronegativity, and lone pairs also contribute if the dipole moment vector points in the same direction. Dipole moment, polar diatomics. So I talked about the idea that this could be dependent on the separation between the two dipoles. So for symmetrical electron distribution, we have a non-polar molecule, and this is going to be a homonuclear diatomic type thing. So like, for example, chlorine molecules, Cl2, hydrogen molecules, H2, things like that, which are homonuclear diatomics. Both atoms in the molecule are the same. So it's homonuclear, nuclear meaning nucleus, homo meaning the same. So homonuclear, diatomic, diatomic meaning two atoms. Asymmetric electron distribution means we have a polar molecule. It means it will have an absorbance in the IR. So this is going to be a heteronuclear diatomic. And then the polar molecule will have an associated electric moment, or an electric dipole moment. So an electric dipole moment is going to be a representation of this uneven distribution of charges across the molecule. So this dipole moment has a mathematical derivation. So this dipole moment can be equal to Q times E times D. So Q here is the point charge, or the charge distribution. So that's going to be the charge distribution in a particular bond or molecule. E is going to be the electron charge in coulombs, and D is going to be the internuclear separation. So like how far apart are the two atoms which are involved in a particular stretch. So let's do an example calculation of the charge distribution of HCl. So HCl is hydrochloric gas in this sense. If we dissolved it in water, it would be a particularly strong acid, hydrochloric acid. But if we just have it in the gas phase, it's not dissociated. It is a single molecule, which happens to be polar because the chlorine's able to pull the electron density towards it in the bond. So the dipole moment here is 1.08 D, where D has got this representation. The HCl bond length is 127 picometers, or 1.27 angstroms. Then the dipole moment is going to be, or sorry, the mu is going to be equal to QED. And so then we can calculate that using what we know, where we know the internuclear distance, we know E, which is the charge of the electron, and we know Q, which comes here from our dipole moment. So if we want to know Q, then the charge distribution, so the dipole moment is 1.08 D. So sorry, we knew not Q. So Q is what we want to find. So we fill in our values here. 1.08 times 3.336 times 10 to the minus 30, which is going to be approximately equal to this. fill this in and this into our equation, which has been rearranged. This equation has been rearranged. D, we've converted from picometers into meters. And then, so we've got everything in the same units. And then Q is going to be equal to this, the solution to this problem. And then, so it'll give us Q, the charge distribution, around about 0.05, which means that this is quite a polar bond. So what does this mean for the charge distribution of HCl? Well, what does a Q value of 0.05 mean for HCl? It means about 0.05 electrons have been transferred to chlorine from the hydrogen. So a sizable amount. So what ends up happening is that our dipole moment has moved so that we have somewhat delta negative on the chlorine and a somewhat delta positive on the hydrogen. And the dipole moment then points in that direction of the arrow, which is the standard IUPAC definition. It's kind of a definition more used in physics. In chemistry, we often draw the arrow the other way, going from the positive end to the negative end. So by IUPAC convention, the dipole moment goes from negative to positive, contrary to chemical tradition. Chemical tradition typically would draw the dipole moment for this bond HCl like so. Typically, we draw the arrow like this with a little cross on the positive side. So that's like a plus sign. So it's like the positive part. And then the arrow points towards the negative part. But in IUPAC definition, the dipole moment goes in the opposite direction, which is also more standard in physics. Molecular dipole moment. So polarity is a molecular property. For polyatomic molecules, the dipole moment is the sum of all bond dipole moments. Lone pairs can contribute to dipole moments, and dipole moment acts in the direction of the vector quantity. The oxygen has a lone pair in water, so water is bent via VSEPR theory, if we recall back to general chemistry courses. And the vectors representing the dipole moment of each bond do not cancel each other out, and thus water is going to be polar. So the lone pairs here and here add electron density here, which makes this somewhat more negative than this. And so we end up with the dipole moment pointing this way from negative to positive according to the IUPAC theory. So polyatomic molecules, the dipole moment is the sum of all the bond dipole moments. So generally, once we have a dipole moment in our solution, we will see alignment of the dipoles. So a positive, negative, positive, negative. So negatives and positives associate to each other. We do not see negative and negative associating. If we put them in between two, like inside of a circuit, we will see that the negative ends align with the positive electrode and the negative parts align, or the positive parts of the molecule align with the negative electrode. And so we end up with just general alignment of positive, negative, so on. And we can even have ions. We see that the molecules which are polar also align with the particular local charge of the ions. So how did we get the dipole moment in water? So the water dipole moment can be determined from its structure. Remember that the dipole moment of a molecule is based on the total dipole moment of the different bonds and the direction in which the dipoles of those bonds point. So the electronegativity difference of oxygen and hydrogen is 1.2 electrons for each of the hydrogen-oxygen bonds. So this was calculated from Pauling electronegativity. So the bond dipole moment of OH bond is given to us as 1.5D. So H2O is not linear, so we need to take 104.5 bond angle into account. So the net dipole moment then can be calculated as so. So if the dipole moment of the OH bond is 1.5, then that's going to be multiplied by the angle that it makes with the dipole moment. So we know that the dipole moment points along this way here, 104.5 for water. Then we are going to have to correct our dipole moment so that it is in line with this vector. So this dipole moment is aligned halfway between the two bonds here. So this is 104.5. So it's going to be halfway to that. So that's why it's 104 divided by 2 for the cosine of that angle. So because we're going this way, and then times the dipole moment 1.5 times the fact that there are two of them pointing in the, well, two of them pointing in roughly the same direction after we correct for the angle. And we end up with a dipole moment, a net dipole moment for water of 1.84 D. Polarity and molecular structure. So a molecule can have polar bonds, but can still be non-polar. If a molecule is completely symmetric, then the dipole moment vectors on each molecule will cancel each other out, making the molecule non-polar. And so a molecule can only be polar if the structure of the molecule is not symmetric. So we see that over on the right here. So carbon dioxide is the one on the top, CO2. So it has polar bonds. Carbon and oxygen have different Pauling electronegativities. These Pauling electronegativities mean that carbon will be slightly more positive than oxygen. And that means that the dipole moment, as you can see here, written with the chemistry tradition from the positive to the negative, although the IUPAC dipole moment will go like this in the opposite direction. So these bonds are both polar. However, because this molecule is perfectly linear, as we know from VS-EPR theory, then there is no net dipole moment, because the dipole moment which points this way and then the one that points in the complete opposite direction, 180 degrees away, those cancel each other out. Now, it doesn't always need to be 180 degrees. You can have other molecules which have got no dipole moment. Like, for example, we saw before maybe a BF3. So that's a trigonal planar molecule. So all of these dipole moments, they point in 120 degrees. So they point in different directions from each other, but every angle is 120 degrees, which means that they all will cancel out. So it doesn't necessarily have to be a linear molecule. However, water, as we've seen, has got the bent structure. So that's because of the lone pairs on the oxygen. So from VS-EPR theory, we know that water has this shape. And so the dipole moments generally point in the same direction. And so there will be a net dipole moment for this molecule. So a quick thinker for us. Do we think any of these are going to be IR active? So I encourage you to take a moment and pause the video and see if you can just determine, before I reveal to you the answer, which one of these will be IR active and which will not, based on the things that I've told you about what is necessary for an IR absorption. So we have nitrogen N2, carbon monoxide CO, carbon dioxide CO2. So their names are given, their structures are given beside them. So they're atoms which we have mostly, like they're molecule types that we have mostly encountered. Okay, so let's start to think about it. Let's go through it. So the top one, nitrogen. So nitrogen is made up of two nitrogen atoms. That makes it a homonuclear diatomic because it's got two nuclei of the same type. So it cannot, in fact, have a dipole moment because the electrons will be shared equally. So nitrogen will not be polar, and so nitrogen will not have a dipole moment. So nitrogen will not be IR active. Carbon monoxide then, so that's CO. So this carbon and this oxygen are different. They have different Pauling electronegativities, which means that since carbon is less electronegative than oxygen, oxygen is closer to fluorine than carbon is, then this is going to be somewhat positive and this is going to be somewhat negative, which means that our dipole moment is going to go like this. And then that means we have a dipole moment, which means this carbon monoxide will be IR active. Then the last one, carbon dioxide. It's a linear molecule. It's got two carbon oxygen bonds. We just learned that carbon oxygen bonds could be polar. So maybe this is IR active. It's not going to be IR active because remember that the dipole moments here are canceling each other out. They're the same and they're pointing in opposite directions. They totally cancel each other out. So no dipole, yes. and IR carbon dioxide is not IR active. That's no. That's a mistake. So vibration and rotation transitions are quantized. They have well-defined energy gaps giving sharp lines in the gas phase. For most molecules, the energy differences between vibrational states are in the mid-IR. So we can see here for water, in the gas phase, we've got a very, very sharp spectra here. Various different lines. So this is transmittance percent on the left-hand side, wave number down here. So you can see here that they're very sharp lines, well-defined. We could actually, we have this kind of space in the middle here, which is where the Q band is. Water doesn't have a Q band, but that's not the topic of this discussion. Each one of these lines represents a transition of the stretches of the gas phase water molecule. And so we can actually resolve these pretty well, and we can actually assign them. But if we put the gas phase molecule into the bulk phase, so we have many, many water molecules interacting with each other, what we'll see is that the interactions between them will cause the lines to disappear. And so the liquids and solids, the lines will disappear due to the intramolecular collisions and interactions. So what happens here is that these transitions cause these collisions and interactions cause alternative energy pathways to occur and cause changes in the energies of the vibrational levels, and just really confuse the spectrum, because you've got so many molecules all having the same kind of vibrations, releasing their energy in different ways via different rotational lines and different vibrations, rotations, collisions, what have you, that it just causes this incredibly complex spectrum. Molecular vibrations then have several different types. So we have stretches, we have stretches and bends are the major ones. So stretches can cause a change in bond length, and bends can cause a change in bond angle. So the top ones in the box are the stretching vibrations. So those are symmetric and asymmetric. So symmetric symmetric vibrations are those in which the movement away or towards a central nucleus are going to be in sync, and asymmetric is whenever they're out of sync. Then for bending vibrations, we have in plane rocking, so kind of goes like that. Scissoring go together. Out of plane wagging, so one goes forward, one goes back. And out of plane twisting, it's kind of like forward and back and rotate, like forward and back and around. So there's 4 different bending vibration types, and then so forward. So they go forward together and they go back together. Out of plane is they go opposite directions. Sorry. So here they're either coming towards the plane or out of the plane. So out of the screen or into the screen. Here, one is going out and the other is going in alternately. So those are the 6 main types of vibrations. So typically, the way that we'll deal with this is by using classical vibrational motion. So what we will do is we will consider that the 2 atoms are in fact going to be attached by like a spring. So it's going to be classical motion. So they're going to be known as what's called a harmonic oscillator. That's not actually how they work, but it's a good way to start. So if we have, for example, 2 atoms separated by a distance, we have, say, for example, a carbon atom here and a hydrogen atom here. So the carbon is our fixed position because it's much heavier than the hydrogen. So this hydrogen will oscillate backwards and forwards according to harmonic motion, if this were a harmonic oscillator, where F is going to be the force required to displace this hydrogen atom. So it's going to be equal to minus ky. So this is what's known as Hooke's law. So K here is a spring constant for the hydrogen atom. So there's a particular constant for this particular system, the CH system. And so the oscillation here is Y. So it's the displacement really from the average position here at 0. It's going to either be negative towards the carbon or positive away. So the harmonic oscillator can be further seen here. So the frequency of the vibration can be approximated by this. So the vibrational or this frequency is equal to 1/2 pi c. times the square root of K over mu. So that looks like a pretty scary equation, but if we break it down a little bit, it's not too bad. So mu bar is the average vibrational frequency. So it's the average point at which all of the molecules that are being measured have the same vibration. So they all have the same CH vibration at a particular wave number. Say it's, I don't know, 1500. That happens to be the average. There may be some which are lower than 1500. There may be some which are greater than 1500, but the average will be around about 1500. And so that will be equal to 1 over 2 pi c, and then that will be times K over mu, where mu is the reduced mass in kilograms, K is a force constant. And so we can see the force constant for single, double, and triple bonds are here. So the force constants get larger, i.e. it's harder to stretch the bond the more bonds that we have. So if we think back to our other chemistry courses, we learned about single bonds, double bonds, and triple bonds. So for example, we can have a carbon-carbon single bond, which is just the sharing of 2 electrons, carbon-carbon double bond, which is the sharing of 4 electrons, and a carbon-carbon triple bond, which is the sharing of 3 pairs of electrons, 6 electrons. So the force constants get larger. So single bonds are easier to displace than double bonds, which are easier to displace than triple bonds. And so those are the force constants around about those values. Then selection rules state that the delta V, so the change in plus or minus 1, must be plus or minus 1. So this is an additional requirement to dipole moment change. So there's a selection rule which states that the change in the vibrational energy level must be plus or minus 1 level at a time. Okay, so the average frequency is 1 over 2 pi c. So pi is pi, and c is the speed of light. K is the force constant of a particular bond, and mu is the reduced mass of that particular bond, which is the product over the sum, if I'm not mistaken. Yeah, product over the sum. Okay, so here is this is the last thing that we'll deal with today. This is a sample calculation of the harmonic oscillator type. So we're going to do it for this bond, the C double bond O bond. So the carbon atom has a mass in kilograms of this. So the important thing is that we often deal with these masses in kilograms. So the mass 1 of the carbon atom, so that's going to be M1. So it's going to be 12 times 10 to the minus 3 kilograms per mole over the number of atoms in a mole times 1 atom. So that gives us the mass of a particular carbon atom. Then for oxygen, we do the same. So the mass is going to be 16 times 10 to the minus 3 kilograms per mole, because usually they're 16 grams per mole. So 6 times 10 to the 23 atoms per mole gets a mass of this for oxygen. This is our mass for carbon, remember. So the reduced mass then is going to be the product of these two values over the sum of these two values, which will give us the reduced mass of 1.1 times 10 to the minus 26 kilograms. And so here we have the equation that we had from the last page where we talked about the harmonic oscillator as a good model for the stretching vibrations of a particular bond. So we put the values in here and we get 5.3 times 10 to the minus 12 s per centimeter, and then multiply that by this is the reduced. Okay, so this is the 1 over 2 pi c, and then this is our K force constant over mu. So K, this is a double bond, so we got the 1 times 10 to the 3 N per meter from the previous slide, and then that will give us a value here of about 1600 wave numbers, which is pretty accurate. Carbonyl stretches, these C double bond O stretches, that's called a carbonyl, are usually found in the 1600 to 1800 wave number range. So this has been the harmonic oscillator for calculation for a carbonyl bond. CO double bond. So like that's really a pretty accurate estimation. So, okay, so we'll leave it there with the harmonic oscillator for now. Next time we'll talk a little bit more about the way in which these vibrations can change based on the particular molecule that they're in. So thanks for watching.